Hello and welcome to my YouTube channel Petro Intelligence. My name is Shahid Khan, and I am a chemical engineer. Today we will discuss cooling water systems. I don't know how ordinary people, lacking an engineering background, take care of their swimming pools. Unless you have lots of time, money, and a degree in water chemistry, do not buy a home with a pool. One thing pool and process cooling water towers have in common is sludge. Perhaps you have driven past a refinery cooling tower with frothy, white foam billowing from its top. That's caused by the following sequence of events. 1. A tube leak develops in a process condenser. 2. The process side hydrocarbons leak into the cooling water return line. 3. The hydrocarbons in the circulating warm cooling water, 70 to 100 degrees Fahrenheit, promote the formation of algae. The algae die, settle out on the cooling water distribution decks, and form a sludge. The sludge also fouls heat exchanger surfaces and the cooling water distribution piping. 5. The cooling tower is now shocked with chlorine to establish a chlorine residual of a few ppm. If the cooling tower is really dirty, this takes lots of chlorine. 6. The dead and dying algae mix with the air flowing through the cooling tower to form froth. To maintain a clean cooling water system requires the maintenance of a chlorine residual content of a few ppm. Organic material leaking into the cooling water consumes chlorine. Without a residual chlorine content, an organic sludge will form. Thus, the prerequisite for maintaining good heat transfers in cooling water exchangers is to eliminate hydrocarbon leaks into the circulating water system. Locating exchanger tube leaks. Open the high point vent on the top of the channel head. I am assuming water is on the tube side of a horizontal shell and tube exchanger. If the exchanger is elevated by 30 or 50 feet, there may be no water pressure at this elevation. If so, temporarily close the cooling water outlet gate valve part way to push the water out of the vent. Now take the gas test meter, the one used by the operators to issue entry permits to vessels, and hold the sample probe above the water stream to test for hydrocarbons. Do not just plug the leaking tube and start back up. You need to determine the mechanism of the failure. The bad tube has to be extracted from the tube bundle. This is a somewhat difficult job, usually requiring an outside contractor. When you inspect the failed tube, it may well appear that 99% of the metal loss is inside the tube on the cooling water side. This suggests that the failure is associated with waterside corrosion. However, if the metal loss is very localized, the problem is on the shell side. Process fluid has jetted through a pinhole leak. The resulting high localized velocity on the tube side creates areas of low pressure inside the tube. Oxygen dissolved in the cooling water can flash out of solution and corrode the surrounding surface of the tube. The problem I'm describing is called erosion corrosion promoted by cavitation. Unless there are signs of general corrosion, thinning, pitting, inside the tubes, large, localized tube leaks are due to shell side, process fluid problems. You cannot draw any conclusions unless the leaking tube is first extracted from the tube bundle. Tube side fouling. Sea water fouls rapidly above 130 degrees Fahrenheit. Circulating cooling tower water may cause excessive rates of salt deposits at temperatures above 120 degrees Fahrenheit, depending on the cooling water quality. One common cooling water hardness deposit is calcium carbonate. Just as with a boiler, we need to blow down some percentage of the circulating cooling water to control the total dissolved solid content of the water. The rate of blowdown is not adjusted based on the water circulation rate, but on the rate of water evaporation from the cooling tower. In many plants, the required blowdown rate to meet the TDS content of the cooling water is 0. That's because of leaks and losses in the circulating system. A large percentage of fouling deposits on the cooling water side of exchangers are manganese. This is mainly a result of biological activity, rather than contamination of the cooling water system makeup water. Effective chlorination will suppress such fouling with manganese salts. One of the mistakes I have made in the past is due to air accumulation in the channel head shown in picture. That is, I've confused the effect of trapped air with fouling. Especially on startup, air may be trapped both above and below the pass partition baffles. The air can fill some of the tubes, especially at lower tube velocities, and effectively reduce the exchanger surface area. Opening the vents on the channel head to vent out accumulated air is a good method to restore lost cooling capacity. Initially, I had confused this lost cooling capacity with fouling. Changing tube side passes. Once a plant changed a water cooler from 2-pass tubes to 4-pass tubes shown in picture, meaning that the water traveled through half the number of tubes per pass. The water traveled twice as far, as it now went through the tube bundle 4 times. The objective of this change was to increase the water tube side velocity. Higher velocity means less fouling. But higher velocities are not possible, especially if the water has to travel further, unless the delta P also increases. Most unfortunately, the delta P on water-cooled exchangers cannot increase. It must remain constant regardless of the exchanger configuration. Let me explain. Let's say your seawater pumps develop a 40 psi discharge pressure. The seawater return line operates at 5 psi. The pressure drop of seawater flowing through the exchanger is 35 psi, regardless of the exchanger geometry. If the water flow is restricted by increasing the number of tube side passes, then both total water flow and the tube side velocity will decrease. When plant changed from 2-pass to 4-pass, the water flow decreased from 1 million pounds per hour to 350,000 pounds per hour. The method of calculation to derive the lower flow is somewhat complex. The calculations take into account that the water has to flow twice as far through the tube bundle, and that there are only half the number of tubes available per pass, but that the water pressure drop must remain constant. Due to the lower flow, the temperature increases of the seawater also went up. 2-pass, 70 to 100 degrees Fahrenheit. 4-pass, 70 to 150 degrees Fahrenheit. At 150 degrees Fahrenheit, the cooling water precipitated hardness deposits. The hardness deposits restricted water flow. The restricted water flow increased the water outlet temperature. The increased water temperature reduced the water flow. The reduced water flow, but perhaps they had made the point. They changed back to the 2-pass configuration. Kindly compare this story to lecture, shell and tube heat exchangers where tube passes were increased. Cooling tower pH control. Effective chlorination of circulating cooling water requires proper pH control. Maintaining proper alkalinity also aids pH control and thus also improves the performance of chlorine in suppressing biological activity. A normal pH target is 6.5 to 7.0. If the pH rises well above this target, the cooling water basin becomes brown and murky. I guess that's because the iron salts dissolved in the water precipitate out of solution. What I know for sure is that heat exchangers throughout in one refinery fouled rapidly due to operators accidentally over-injecting caustic into the cooling water return line. They quickly restored the pH with sulfuric acid. Operators overshot the target and drove the pH down to 4. The water became clear, clean, and corrosive. Leaks sprang out throughout the carbon steel water supply and return piping. Sulfuric acid is used because the pH of water naturally increases due to evaporation of water in closed systems. Wooden cooling towers. Most older cooling towers in the world are constructed of wood. The interior of the tower is filled with wooden slates. The lignite in these wooden slates is removed by the circulating water and causes the slates to break. The failure of the slates degrades air-water contacting, which raises the supply water temperature to the process units. The two things that will accelerate the rate of lignite loss from the wooden components of the cooling tower are High cooling water return temperature. Above 130 degrees Fahrenheit is considered excessive. High residual chlorine levels. Above 2 or 3 ppm is considered excessive. Occasionally shocking the tower with chlorine is common practice but should be done less than once per week. Backflushing and air rumbling. The operators in a refinery used to blow nitrogen into the water inlet line to coolers. It's safer to use nitrogen than air, in case there is a tube leak. They just coupled a 1-inch hose to the water inlet nozzle and blew in nitrogen for 10 minutes every day. I call this air rumbling. It helps to clean the tubes. Backflushing is more effective in clearing tubes than air rumbling. The cooling water supply line is closed. A valve draining the water to the sewer is opened on the inlet side of the exchanger. The drain, or backflush valve, has to be at least half the diameter of the water supply piping. Water flows backward through the tubes until the water flowing to the sewer is clear. If the exchanger is elevated more than 20 or 30 feet, it's probable that backflushing is not possible due to the lack of water pressure at the higher elevation. In one refinery, an engineer installed a backflush header pipe using high-pressure firewater to supply pressure for backflushing. Check with your plant's safety division before you make such a modification. Backflushing is much more effective when it is done once a week, not as required. It prevents individual tubes from overheating due to low water flow and plugging off with hardness deposits. Once tubes are plugged with carbonate hardness deposits, the next step is acid cleaning, as such tubes cannot be cleared by backflushing. Acid cleaning. It's best to avoid acid cleaning. pH excursions in the cooling water circulating system are probable. Acid is injected into the water inlet, while a caustic neutralizing agent is injected into the water outlet. Acid cleaning is very effective for the exchanger being cleaned. However, the rest of the cooling water system is subjected to accelerated rates of fouling and low pH corrosion due to acid escaping from the exchanger. This is being acid cleaned. Combating hydrocarbon leaks and improper water chemistry should minimize the need for online acid cleaning. Increasing water flow. Your cooling tower basin is likely served by a number of circulation supply pumps. You may have observed that putting an additional pump online does very little in increasing the combined pump discharge pressure. This means that the total water flow has not increased. For example, 3 pumps on, discharge equals 48 psig. 4 pumps on, discharge equals 50 psig. Cooling water return at grade for both cases equals 10 psig. The delta P for the 3-pump case is 38 psig. The delta P for the 4-pump case is 40 psig. That means the pressure drop through the exchangers and piping system has increased by 2 psi, or 5%. Since pressure drop varies with flow squared, the water flow has only increased by 2.5% by starting the 4th pump. This does not usually indicate a pump malfunction. More likely, it is an indication that all 4 pumps are operating on the flat portion of their pump curve. Watch my lecture, Centrifugal Pumps, Fundamentals of Operation. To get more water flow, you will need to reduce restrictions in the circulating system. In a refinery, the problem was lack of effluent cooling on a hydrotreater. Operator decided to increase cooling water flow through the effluent cooler by reducing the water flow through exchangers throughout the rest of the refinery. He reasoned that there was a single cooling tower that served the entire refinery. All the cooling water exchangers were piped up in parallel. Thus, if he reduced water flow through some of these exchangers, he would divert more water to the hydrotreater effluent cooler. He monitored progress by looking at both the process and water effluent temperatures on the hydrotreater cooler. He throttled back on the cooling water flow to dozens of exchangers. Several of these water coolers had not been used for years, but no one had bothered to block in the water flow. He spent most of an afternoon on this activity. Based on the combined water temperature returning to the cooling tower shown in picture, he had reduced the total circulating water flow by 20%. But the water flow to the hydrotreater effluent cooler had not increased at all. Why? Because he was running on the flat portion of the cooling water supply pump performance curve. Was there any reward for his efforts? Yes. The amperage load on the cooling water pump motor was reduced from 60 to 50 amps, an improvement that was of no interest to manager. Piping pressure losses. For water flowing through clean pipes, delta P equals 0.15 times V squared divided by ID, where delta P equals pressure loss per 100 feet of pipe in PSI, V equals velocity in feet per second, ID equals pipe diameter in inches. The idea is to compare the measured and calculated pressure losses in the water system. In seawater systems, the pipe lining may tear loose and restrict the water flow. An engineer once found an isolation gate valve, mostly closed, buried under a road crossing. It was a 30-inch valve. A maintenance crew spent 2 days working it open. The water flow only increased by 8%. The plant manager was quite angry. So, the manager initiated a project to install a new 500 horsepower pump to run in parallel with the existing two 500 horsepower. As the existing pumps were already running on the flat portion of their performance curves, the incremental water flow observed when the new pump was commissioned was 2%. Cooling tower efficiency. Two types of cooling towers are in widespread use. Natural draft as shown in picture. Induced draft shown in picture. The giant natural draft towers are used in Europe and in nuclear power plants in the United States. I've only worked with these towers in one refinery, and their performance was poor. Airflow is generated by the air inside the tower being heated by the warm cooling water. Also, the molecular weight of the evaporated water is less than the molecular weight of air. A few tenths of an inch of water draft may be developed. The much smaller induced draft cooling towers are used in process plants. Airflow is generated by large induced draft fans. Regardless of the type of cooling tower, the same criterion is used to gauge performance, the approach of the cooled water temperature compared to the air wet bulb temperature. Wet bulb temperature. Water is not significantly cooled by exchanging sensible heat with cold air. Most of the cooling results from the humidification of the air. If you live in Dubai, your home is likely cooled with a swamp cooler rather than with a Freon compressor. The water partially evaporates as it mixes with the dry air. The latent heat of evaporation of water is 1000 BTU per pound. If 2% of the water evaporates by contact with the cold air, the water loses 20 BTU per pound. The specific heat of water is 1 BTU per pound per 1 degree Fahrenheit. Thus, the water will be cooled by 20 degrees Fahrenheit by evaporation. It's mushroom soup story again. Converting the sensible heat content of the water into latent heat of evaporation of the water. But for the air to carry away the evolved water vapor, it has to be below its dew point temperature. To gauge how efficiently a cooling tower is working requires two temperatures. The cooling water supply temperature leaving the basin. The wet bulb temperature of the ambient air. The air temperature itself is called the dry bulb temperature, which is not important. To get the wet bulb temperature, turn on your TV. Switch to the weather channel. Read the current dew point temperature, which is the same as the wet bulb temperature. Alternatively, measure the wet bulb temperature as follows. Take a small piece of fabric and loosely wrap the bulb of a thermometer, leaving a short tail of the fabric dangling below the thermometer. Dip the tail of fabric into water so that the water soaks all the way up the fabric that is covering the thermometer bulb. Now measure the ambient air temperature using the thermometer with the fabric wrapped around its bulb. This is known as the wet bulb temperature. It will be lower than the dry bulb or ambient air temperature because the water vaporizing off the fabric cools the bulb of the thermometer. Calculate the performance delta T. This is the difference between the water leaving the tower and the wet bulb temperature. You can judge the performance of the cooling tower as follows. If the performance delta T is 5 degrees Fahrenheit or less and the temperature rise of the water, the return minus the supply, is 15 degrees Fahrenheit or more, tower performance is excellent. If the performance delta T is 8 degrees Fahrenheit or less and the temperature rise of the water, return minus supply, is 30 degrees Fahrenheit or more, the tower performance is also excellent. If the performance delta T is 10 degrees Fahrenheit and the warm water coming back to the cooling tower has increased in temperature by 15 degrees Fahrenheit or less, performance is poor. Note that the 15 degrees Fahrenheit is called the water temperature rise. If the performance delta T is 15 degrees Fahrenheit and temperature rise of the water is 30 degrees Fahrenheit, tower performance is poor. In the older, induced draft wooden cooling towers, a common problem is that the wooden slates have broken up. There is usually an access inspection door at the base of the cell. Often, the water distribution holes are plugged or there are large holes broken into the deck. Water is not supposed to overflow around the outside of the cooling tower. On some cooling towers the fans are driven by belts, which can slip, or the fan blade pitch is set too low, low being less than 15 degrees, maximum being 23 degrees. That's all, gentlemen. If you like my video, please follow my YouTube channel Petro Intelligence for more videos. Good day and good luck.